let's start talking through this stuff here. So like I said, some of this stuff is very similar to stuff we worked on in previous sections where we're dealing with like the radicals and that kind of thing. When they say something with a radical, the radical is just that root of something. So like square root or cube root or whatever, that's just the name of that symbol. It's called a radical. So when it says definition of that n in the root there and then x, when x is greater than or equal to 0, so just saying it's a positive number basically. They give that thing as when x is a non-negative number, so that's the part that's greater than or equal to 0 or whatever, and n is an integer, n is greater than or equal to 2, then when we have that nth root of x or whatever, we know that that's the same thing as like if it was x to the power of 1 over n. So we talked about that before where like if you had like, you know, just square root of x, that's the same as x to like a half, right? Remember we talked about that in previous sections. That's basically all that's saying. Now, they're going to ask on your assignment for you to write it in different ways. So if they want you to leave your answer as radical form, this is what radical form is, where you leave it with like a square root or cubed root or whatever. If they want you to write it as like a rational exponent, the rational exponent is when you switch it to where it's got like the power of, you know, a fraction or something like that, or just a regular number, but it's something with a power, okay? Geometric mean is probably something that's new to us. So you guys remember regular mean, right? Where it's like the average where you add everything together and then you divide by how many numbers you have in your list. So geometric mean is a different way of doing something similar to that. So a regular mean or like a regular average, that's actually called the arithmetic mean. We use that when numbers are kind of similar to each other. So maybe you had like 10, 12, 15, 20, something like that where they're all really close. We use a geometric mean when the numbers we want to try to find something about, like a measure of center, we want to use it when the numbers aren't really close to each other. So say maybe one number is like 20, but then the next number is like 100, and then there's a number in the thousands or something like that. When our numbers aren't close together or like quite dispersed or whatever there, what you want to do is you can use a geometric mean instead because it doesn't let outliers affect it as much. And outliers we'll talk about more next year, but it's basically big or small numbers that affect your values. So what you do to find the geometric mean is you take all of your numbers in your list and you multiply them. Then whatever you get for the answer there, you take the root of that answer and you do the root of however many numbers were in the list, okay? And one of these examples we do is based on that. So let's switch to our example sheet then. And the first question here wants us to do that. It wants us to find the geometric mean of this list of numbers here. So you can kind of see there how we've got, you know, so it's populations for 1 square mile regions in the United States. So this is probably like a place like maybe like Alaska or something like that where, you know, not very many people are living. This 45,000 would be like a bigger city where there's lots of people living in a small area. So obviously, you know, the United States is all dispersed or whatever, so those numbers are very spread out. So to find our geometric mean, what we want to do is we want to take every single one of these values and multiply them. So it's going to be a really, really big number. So it'd be like 47 times 68 times 159 times 2,215 times 8,715 times 10,512, should have wrote smaller, times 12,130 and 45,312. And then once we find that value, we want to do the root of it, and the root we use is however many numbers are in the list. So since there's 8 numbers in that list, once you get this answer, you're going to take and you're going to do the 8th root of whatever that answer is, okay? And again, we just get this 8 because it's however many numbers are in the list, okay? Like I said, we're going to get a really big number here. I would just type all of these all in at once when I multiply, so like do like 47 times 68 times 159 times 2,215 times 8,715 times 10,512 times 12,130 times that 45,000 number. And again, you're going to get a really big number there when you do that. So like mine, you remember how when it's the e like that scientific notation where it's this value times 10 to the 25th power, which means you have like 25 spaces you got to fill in with all those numbers. That's basically what that means. So instead of like writing that all out, what I do is I just keep it on my calculator. And now I want to do the 8th root of something. We don't have a button for 8th root. We do for square root, right? Because our square root button's that little one there. But we don't have an 8th root button. But we know 8th root is the same as taking something to the power of 1/8, right? So what I would do is I would just hit power, and then I put it in parentheses 1 divided by 8. I think if you have the new ones, it just raises it up and you don't need it in parentheses there. But if I just hit that power, it will take my previous number and just bring it down there. So that ANS just stands for answer that was previously listed. So just do it to the power of an 8th, hit enter, and that should give you your approximate number there. Okay, so the geometric mean of that is approximately, I got 1,656 point, let's just go 44. And that would be, we're measuring in population per square mile, so like people per square mile or something like that. But you just multiply them all and then take whatever root of whatever your product was. Okay, and then these next two that came with the book, whatever calculator the book is using for some of this, it's got these other settings on it that sometimes they want you to mess with. We don't need to mess with these settings. We can just do this out on our own, but basically it just wants you to set it to like real number mode or complex number mode. Basically, I just wrote off to the side here. This one we're looking for all of our real numbers. This one we're just looking, or this one we're just looking for real numbers. This one we're looking for all of our numbers. Okay, so remember how we have like the I and stuff with stuff sometimes? That's basically what that's getting at. So here, if it wants us to evaluate like the 4th root of 2,401, you would just take, so 4th root of 2,401 would be the same as taking that 2,401 to the power of a 4th, right? So we just do that on our calculator. So 2,401 to the power of 1 divided by 4, and that gives us 7. And then knowing what we know about roots, when we do roots, and this is a positive, or not a positive, an even number, what do we also have to have with the 7? The plus or minus thing, right? Because couldn't we put in there a positive 7 or a negative 7? Because if we took negative 7 multiplied 4 times, wouldn't the negatives all become positive? Get us back to that? Yeah, so we're going to focus more on the odd even stuff with this section. So if it's an even, you're going to have both that plus or minus there, okay? And we'll do some more of that in the next couple examples. So now, when we're doing all ones, what's the other thing we add? I think this was actually on our test screen the other day. What's the other thing we add to this if we want all of them versus just the real ones? The I stuff, right? So we still have this plus or minus 7, because that's still part of our answer for the all of them. But then we also have that plus or minus, and then the 7 with the I, because you can also have those complex ones. So very, very similar to some stuff we did last chapter. Okay, and then we got one more theorem to talk about, and then we'll do the last couple examples. Okay, so this one, this part kind of looks complex here, but it's not as complex as you think it is. So this root of a power theorem, like I said, we kind of talked about this stuff a little bit before, where when you've got something like this, you can rewrite it as like a fraction. So if it's something that's underneath that root, that's just like a regular power, so that would be like just a power of m, just a regular number. So that would be like the top of our fraction. And then whatever you're finding the root of, that root value that's kind of on the outside there, that would be like the bottom of our fraction, okay? So if you ever needed to turn that into like one thing, which again, we've done a little bit of that before, you can kind of just put it together as that fraction, just whichever one's underneath it is the top, and then whatever the root one is, that's the bottom. Now another thing they're going to kind of start doing in this section to us is they're going to have us find like square root of square root of square root. What you can do is instead of having all of those roots written out, you can just think of this as, you know, if my inner one there's a square root, just switch that to the power of 1/2. Then that next one is a square root, that's the same as a power of a half. Outside one's a square root, that's the same as a power of a half. And then do you remember what we do when we do like a power of a power of a power, what we do with those fractions? It's a power of a power of a power. Add, subtract, multiply, divide. Multiply them. So what you would do is it would be like a half times a half times a half. So like 2 times 2 is 4, right? And then 4 times 2 would be 8. So wouldn't that be the same as like x to the 8th? That's basically what they're kind of getting at with something like that. So there might be some problems like that. And then these next two examples are ones that I added in because I thought they would be helpful for us. So these next two here, like I said, they did some here where it's like roots of roots or whatever. So here it wants us to rewrite, looks like there's 1, 2, 3, 4 of those square roots there. It wants us to rewrite that using rational exponents. So again, if they say rewrite it with rational exponents, that's like power of our fraction there. And then they want us to figure out, is the expression the nth root of 10, and then justify your answer. So let's rewrite it first here. So if I've got 1, 2, 3, 4 of those square roots, that would be the same as if I had like 10 to the half. So that's one of them. Another set of parentheses to the half. Another set of parentheses, half. And then another set of parentheses there and a half. Really, I probably didn't need the parentheses around the original 10, but same difference. So then if I think of that like my one I was just thinking of, if I do a half times a half times a half times a half, just 1 on the top because it's all 1s multiplied. 2 times 2 is 4, times another 2 is 8, times another 2 would be 16. So if we had to rewrite this with the rational exponents, this would be the same as 10 to the 16th. So that would be kind of our rewrite there. And then it says, is this an expression, or is this expression an nth root of 10? Justify your answer. This is where it gets a little bit confusing. So if we have that 10 to the 1/16th, they're just trying to figure out, okay, if we, did that out and multiplied this value 16 times out, would it end up being 10? And it should be, right? Because if we took this value here, so let's just say yes to start, and then we can say 10 to the 1/16th is the 16th root of 10, and we know that because, that's the same as roots. And then we could say, like, because if we took that 10 to the 1/16th times, or did that out times itself 16 times, that should get us back to just a regular 10. Because if we did, that 1/16 times 16, wouldn't that just all cancel out to be 1, and 10 to the first is just 10? Yeah, I don't know. The explanation on that one's kind of weird. The main thing is, can you rewrite that as, the power thing there? Okay, and then this last example here, this is where it's going to get a little bit tricky for us, and you're going to have to kind of use your brains quite a bit. So this here, so they want you to do it without a calculator. I'm going to show you how to kind of walk that out. As long as you're showing me the steps of how you know how to do it, if there's some stuff that you can't divide off the top of your head, you can use your calculator to do some of the division, but I need you to at least show me the factor tree thing that I'm going to show you to break it down. But like if there's some division stuff that you're like, I don't know what this divides by off the top of my head, you can use the calculator to do some of the division if you need to, but try to not just factor it out all the way using that. Try to, use this factor tree thing and show me the work, but I'll kind of walk you through. Now, an important thing to note here when we're doing this, we didn't focus on a whole lot of this last chapter, but we're going to focus on more of it now, is there is a difference in our answers when we're doing a root of an even number versus an odd number. Okay, so here I have 4 is an even number, so I kind of highlighted that so I know that that's important, and then 3 is an odd number, so that's important as well. So we've talked about this briefly before, but anytime you have a root of an even, you're going to do the plus or minus thing. If you have a root of an odd, it's just whatever answer gets kicked out from the calculator or done out. So it's just either positive or negative, okay? So these ones are always going to get the plus or minus. These ones are not, okay? And maybe you even do that. So like under the even one, maybe like write plus or minus. That'll be a reminder. And like I said, I'll show you some examples of that, but that's going to be something important from here on out when we work with this. So what we want to do here, if they ask us to find the 4th root of this number without our calculator, basically what we want to do is we want to figure out which number we can multiply together 4 times and get this number here. Okay, so what we're going to do is we're going to use a factor tree. Do you guys remember factor trees where you've got like you take this number here and you kind of break it like that and break it into factors? Does that remotely seem familiar? No? Okay. So what factors are is they're numbers that multiply together to give you this number. So my first thought here is if this is an even number, what's always a factor of an even number? Like what can all even numbers be divided by? 2, right? So I know that this number here is going to be 2 times something, right? So then what I'm thinking is I'm just thinking, okay, what's half of this number here? So what I do when I'm doing halves is I break it into chunks here. So if I'm just thinking 1,000, what's half of 1,000? 500. And then if I go half of 200, 100, half of 90, 45, and half of 6, 3, and then you just add all those together. So like 500 and 100 would be 600, plus 45 and 3 would be 48, so 6, 48. Does that kind of make sense how I did that, just kind of in my head? And that's easy when it's a 2, because that's, a nice number to break down. But you just break that to 648. Now what we're going to do, so this is called prime factorization. Do you remember what prime numbers are? So prime numbers are numbers where the only factors or the only things that are regular numbers that multiply to be that number are 1 in itself. So like 2 is a prime number because the only nice way to get there would be 1 times 2, right? Like you couldn't take, 5 times something and get that or whatever. So what we're going to do is once we get down to the primes, we're going to circle them because we're going to need those, okay? So now here, this is also an even number, right? So if I take this even number and break it down, I can go 2 again, which is prime. If I take half of 600, 300. If I take half of 40, 20. Half of 8, 4. So that's 324. And then you can just keep doing that out there. So, it's another even one. So you can go 2, and that would be half of 300 would be 150. I'm not going to write all these out because we're going to run out of room. But it'd be like 150 and 10 and 2, so 162. We can go even again. I think I'm going to go 2 on this side, so I don't keep going that one. I'm going to go this way a little bit. So if we go 2 again, half of 100 would be 50, half of 60 is 30, and half of 2 is 1, so 50, 81. And then at this point, we run into our first one that's not even. And you didn't have to do like, 2's all the way out, but 2's is an easy one to divide by. That's why I usually use that as far as I can. But now when I get to 81, not divisible by 2, so I got to use something else. What's something that multiplies to 81 though? 9 and 9, right? So like here, if I go 9 and 9, are either of those prime? No, because what could those break down to? 3's, yeah. So both of those would go down to 3's, and 3 would be prime, okay? So I circle all of those 3's. Okay, so now the purpose of all that craziness there is to come up with all of these prime numbers, because what happens is if I take all of the ones that I circled and I multiply those together, that will get me back to this number here, okay? So what I want to show here, I think I'll do it right here. I want to show that that 1,296 is equal to, and I multiply every single one of those circled ones together. So 2 times 2 times 2 times 2. And I usually do it in order, so like I know all the 2's go together and all the 3's go together. And then there should be 4 of the 3's. And then what we're specifically looking for there is we're looking for groups of 4. And the reason we're looking for groups of 4 is because we were taking the 4th root of this, okay? So what we're looking for is we're looking for groups of 4 that are the same number here. So here, don't I have 4 of those 2's? And don't I have 4 of those 3's? So usually I kind of group it like that, and I know I'm grouping 4 of them together because that power was 4. And then what you do is you're like, okay, well, if I have 4 of those there and 4 of those there, that's the same as that one and that one. So what I'm going to do is I'm going to take one from here and one from here. So 2 and 3. And what is 2 times 3? 6. So that's the root of that is 6. And what do we have to be careful of if this is an even one? Plus or minus. So our true answer there is plus or minus 6. Okay, does that kind of make sense a little bit? And again, there's going to be something like this where you got to break it down and you got to show me. Just show me this stuff out with the factor tree, show me this out here, and give me that. If you just write plus or minus 6, I'm not going to be able to give you credit for that because you got to show me what you're actually doing, okay? Because I know you can just type it in your calculator and get that number. That's not the point, though, okay? Because we're gonna keep building on this. That's why we have to know this, okay? All right, so let's try another one here. This one's not as big as a number, so it shouldn't take as long. I'm going to draw a little line here so I know that it's a separate problem. Okay, so this time I've got cube root of it, and I've got 216. So 216 is my number I'm breaking down. Again, 2/16 is an even one, so we can go with 2 because that's an easy number to divide by. So half of 200 would be 100, half of 16 would be 8, or you could do half of 10 is 5, half of 6 is 3, still 8. So that'd give us 108, right? Circle R2 because that's prime. 108's even. So we could go down to 2, and half of 108 is 54. 54 is also even. So 2, and that would be half of 50 is 25, half of 4 is 2, so 27. And then now we get down to our first odd one here. So 27, we can't use 2. What could we break 27 into instead? 9 and 3 would work. So if I go 9 and 3, 3 is good where that's odd. 9 could go down to 3 and 3. Those are odd. So then we do the same thing out again where we're going to rewrite it with all those primes. So 2/16 is the same thing as we got 1, 2, 3 of the 2's. So 2 times 2 times 2. 3 of the 3's. So 3 times 3 times 3. And then again here when we're looking for groups of things, we're looking for groups of 3, right? Because our root there was 3. So you got a group of 3 there, group of 3 there. And then again, this one actually works out where it's the same numbers here, 2 and 3. So if you got 2 and a 3, you're pulling down there. 2 times 3 would give us that same 6. Now in this case, because that power is odd, we just keep it as that answer there, just the 6. Okay? If it was like if we started with like a negative 2/16, then that'd be a little bit different. But here it's just going to be 6. Okay? And again, we don't have to do that plus or minus thing because that problem is odd. Okay? That's a little bit much. I know that last one's a little bit difficult there. I think there's a handful of questions on the assignment about that. I don't think it's the whole assignment. But the next section, we're going to kind of keep building on that. That's why I want to make sure we're kind of going over it now because we'll get more in depth with that with the next couple sections, okay? So that's your book page there for tomorrow. And then I think tomorrow's worksheet day. So work it out of that for tomorrow.